Are we live? Yes, we're live. All right, so my name is Withad, and this is the first time I'm standing on a stage.
Wow!
So naturally, I've got my best serious glasses on for the occasion, because we're going to have some fun. And thankfully, I have my good friend with me who has been on a stage many times before.
I have. So my name is Christoffer Jerkeby, or Kugg, and I'm really happy to be back here. This is my favorite conference, so I'm pretty stoked. We are going to talk about plain old Java land. We're going to play hide and seek in Java land, and that means that we are going to look for things that can be detected and things that are hard to detect in Java exploitation. And we're going to compare how things are hacked today and how we think things are going to be hacked tomorrow in Java applications. So, how are things getting hacked? As offensive security researchers, it's our job to give pen testers and other risk managers the ideas of how things could be, like give them perspectives or avenues of what could happen. And pen testers, they assess these and make sure to check if they work. And during this presentation, we will show some tools that you can use to actually try this at home if you want to. And right now, we have a problem that supply chain attacks are rampant in interpreted languages. So Python, Ruby, Node.js, and in NPM, you have backdoor packages. They are script languages, which are easy to change. Is it possible this will happen also in Java? So you have attackers who move from being regular exploiters that move into supply chain attackers. If we talk about regular exploitation, conventional exploitation, the idea of a Java application pretty much looks like this. You have internet, where bad people live. You have a reverse proxy from large vendors that funnel data into a controller made in Java, in this case, and that sort of directs traffic to a view, which is a fancy word for HTML or markup languages. And you have this model thing, which is a very fancy word for a database. This is a very simplified architecture view. Usually they're more complicated than this, but it's pretty much what there is. And conventional attacks are based on the idea that someone from the internet attacks, well, the controller or the view or something like that to get data out. However, we are aiming more into this thing here, the build pipeline. So if you're a developer, or if you're helping developers, or you want to assess a developer, this is what's going to happen. So there is a developer laptop that builds code into version control, sometimes called Git or something like that. And there's a build server that builds the code and compiles it into something called a jar, a Java archive. And that's being orchestrated by maybe something called Kubernetes or whatever into a production environment that resides publicly on the internet. And attackers, they want to get to data and usually into this production environment. So it's not a bad train of thought to think that someone from the internet would go directly on the production environment. But we are considering an alternative path. So look at this. If you imagine the build pipeline with dependencies, you have something called a package registry. Our package registry is called Maven, or Maven Central. That's the one we are focusing on. But they can also be a local one. You can have one in your environment. And it's providing open source libraries, usually, to the developer laptop and to the build server, so that you can compile things that are identical on the developer laptop and the build server, and then it ships to production. And supply chain attacks is when someone like Withad here digs deep into his little bucket and plants something in the package registry that starts to grow on the developer laptop, or starts to grow on the build server, or starts to grow in production, something like that. And this is happening right now in a lot of languages. Like I mentioned, in Python, there's been attacks like this, and definitely in Node.js as well. But not so much in Java. We'll show some examples of it, but there are some limitations to it. Okay. I want to show something about RCEs. So RCEs is, well, the conventional attack path, how things are getting hacked.
So basically, I mean, RC, he says, acronyms, but like that's the worst thing that can happen to you, basically. It's the worst shit. That's what you need to know right now.
Right. So it's as bad as it gets, and it means that you're exploiting something from the internet that gives you remote code execution. But you can also compare this to the word arbitrary code execution, which means to be able to execute anything. So the difference between remote code execution, which is the sort of initial foothold, it means that you can only execute things that are maybe possible in that context. And to get arbitrary, it means to do anything. And anything is very bad.
It's even worse than the worst.
So as an exploit developer, we want to get to arbitrary. So we want something that works on all targets. We're thinking like attackers here right now, okay? So we want something that works on all targets. So no matter if this is running on Windows in the bottom or Linux, it should always work. We want something that always works if you're on the right machine. So you need to be careful how you write things. Sometimes it's harder to be an exploit writer than a developer in a sense, because you need to have something that works in many environments. And we call this generic payloads. A generic payload is something that sort of always works. And that means that most Java exploitation happens in known vulnerabilities in known software. That means that there is a known vulnerability in struts2 or something, and someone scans the entire internet for instances of struts2, only this software, and they exploit only that in a certain way. And that's their specialty. A lot of attackers think and work like that. They're rarely specified into going for unknown targets. So if you're a bank or a government agency and you run Java, it's very common in the Nordics. There might be attackers who try to get to you, but they don't know how because they don't have enough information about your target environment to exploit you, even though you might be vulnerable.
Unless you use struts version old.
Right, you use a known software and it's very clear that it's there, right?
CVEs and stuff.
I'm going to try to introduce briefly the two attack vectors that are most common. So insecure deserialization is an attack path towards the controller, where you take input from the user and you try to deserialize it into an object. Doesn't really matter. It looks like this. So this is one of the first exploits for insecure deserialization, and it was introduced on Jackson data bind. The vulnerability first specifies on line 11 something called object. There is something called a gadget. A gadget is a class that we want to serialize. We want to make sure that the server creates one. But the server must have one to create one. So there must already be a templates impl inside this Java application for this to work. This is called a gadget, and the content on the gadget is that translates bytecode. Right? Let's look at another example, template injections. Template injection happens in this HTML thing, the view, when you're mapping input or model data with a template that you created in the view where it says, welcome to my web page, bum, 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 Mr. Christoffer. But Mr. Christoffer is actually template data now. And now we're going to look at Spring Cloud Gateway Code injection vulnerability from 2022. It provides a bit more artistic freedom because you can write actual Java code inside the payload, but what you cannot do is write Java code that's not part of the application, which means that if you have a vulnerability like this, the attacker must know something about your environment to be able to guess what they can write. And the payload here maybe looks a bit strange, but it's doing an exec of bin sh, it's popping a shell. This is the most common generic payload. And the reason why I talked to you before about generic payloads is that attackers tend to want to be able to do the same thing over and over again to save time. So they create generic payloads, which means popping a shell in this case.
Popping shells. Who doesn't like popping a shell? Everybody does it, right?
Everybody does it. And this is a known and classic payload. The previous case of injections, the insecure deserialization, also wants to pop shells. That's also the way to go, basically. So the limitations to RCE is that only classes inside the application you want to attack can be used, which means you need to know the application or guess. And if you guess, you're going to crash the application a few times, which is going to end up in the logs. Or you run runtime.getRuntime.exec. You pop a shell.
Yep.
Thank you.
So when you do that, which is fun, that's going to actually set off quite a few blinking lights if you are a defender. So for instance, if you have a Java process and you are running an exploit, a payload with a system runtime exec, you want your shell, right? You want to do the things where you're comfortable with. This is how it's going to look in the process tree for a Unix system. Your shell, your netcat, whatever, that's going to stick out as a sore thumb. Like, this is not normal. Sure, some Java developers do some weird shit, like that's fine, but like normally Java doesn't spawn out, fork out other processes. This sticks out. So blue teamers, take note. This is very obvious. In fact, this Splunk query, you don't have to take pictures, we'll post it somewhere, but like this Splunk query will basically, it is a detection that will show you when this happens. And this will probably work for most exploits for Java today. So that's it. You're welcome.
And that's it for today. We're done.
We're done, right? No, not quite.
Let's look at the other one.
All right, yeah, sure. So this is an exploit vulnerability that is less than a month old. So it means it's probably in production, right? And this is a cool example because it's not spawning out a sub-process. It's not popping a shell. If you look at this, you don't have to understand all of it, but it's basically loading, using a URL class loader. It loads Java code out of band, downloads your stage 2 Java code, and executes it. Like, that is arbitrary code. Like, I can put anything in there. Not just the gadgets, not just the shell. And it's going to execute within the Java binary, right?
So when we are making this comparison, we want to talk about cost, because the world is about money. As attackers, we want to invest time, which in this case is money. You want to pop as many shells as possible, or not. But you want to do something that's where your work really pays off. So if you're doing security research and you, as an attacker, scan the internet, you want to exploit things, you're doing recon, you're collecting gadgets in the RCE case, you're doing adaptation to this payload, getting to know the target somewhat, and there's plenty of development to make things work stable. There is a certain cost of detection. So imagine you get detected early, because now all the blue teamers in the Scandinavian region are here in the audience, and they're going to use this detection, right? And because of that, they're going to fall back to recon stage again. And there is a certain cost to that. So good for us. And this type of logic means that there might be a future shift to supply chain attacks, we think. So in supply chain attacks, the cost is development once, which for governments who use tax money, well, can mean a lot of development. In the case of XZ, for instance, they had some money to do what they did. You have to put it out there to get it into dependencies. We're going to talk a lot about that. And then wait and just see your beautiful garden grow. And this means, we think, that people who are today capable of doing zero-day RCE or RCE-related exploitation on the internet could easily move into the supply chain world. And we'll show many examples of how that's been done before. We're going to talk about initial access vectors, historical and today. So the goal is to own as many dependencies or as many lines of codes as possible you can, right? So you want to have a tool chain that opens up many options for gaining access. You want to take over packages on the internet and own them. This is what's important in supply chain, in the supply chain world. And one method does not exclude the other. And we see in PyPy and NPM the past 8 years that the attackers have been quite inventive. Once they're getting started, they rarely give up. So if they get kicked out, they take over other packages. And we're going to look at how that looks like. I'm going to wind back the clock, I think, to 2003. when I was young. So there was almost a backdoor in the Linux kernel in 2003 in the function called wait for. Wait for waits for another process to change state. This line of code is pretty hard to detect. Actually, no one found this because of the line change. What's almost yellow there? It says current UID equals 0. 1 equals means assignment. That means that when this if statement runs, you become root. It doesn't check if you are root. I mean, it was completely missed in code review. However, the code was never introduced due to how the version control in the Linux kernel worked back then.
I just want to back down. Like, imagine how bad that is. Somebody just implanted a backdoor in the source code of the Linux kernel.
That means owning
happens.
all the machines.
Yeah,
Literally.
that happens.
Yeah. I cannot say for sure, but I think the attackers were called acid bitches.
Acid bitches.
Yeah. Yeah, what a name, right?
Yeah, hackers.
So, the year after this attack, Acid Bitches made a write-up in the magazine Frack, number 64, if you're interested. They made an article about CVS exploit. It was an exploit that actually was used the year prior with the Linux kernel to get access to their version of Git called CVS. And I think personally that Linus Torvalds, who then wrote Git, was motivated to write Git because he saw that my version control tool does not protect me against modification. During the era, year 2003 to 2010, we have multiple backdoors in source code. Proof FTP, Unreal IRCD, and many other programs get backdoored by acid bitches using exactly this technique. So for years, you could get into any IRC server on the internet using the word acid bitches, or any FTP server on the internet using the word acid bitches.
So for the young audience, IRC, that's like your Discord. Imagine having backdoor access to all of Discord. Yeah.
Yeah, but cool. But these guys were admins on all of them. I wonder how much they helped out. But they published on the full disclosure mailing list exploit after exploit, and they made write-ups of how they did these attacks, because that's what people did in the beginning of 2000s. It's not like that anymore. The spree ends in 2010 when a new attacker enters the scene. I don't think this is Acid Bitches doing this. So Apache.org was hacked using a cross-site scripting vulnerability. And here's a shift, because previously we have these advanced attackers doing advanced C things, and now someone's doing something as mundane as cross-site scripting. This is a request I made the 6th of September, so it's still online. This tiny URL still serves the vulnerability that was used. So if you do a curl, if you click that link, it will try to go to issues.apache.org and gives away your logged-in cookies to the Jira instance that's running there to these attackers who are hosting their stuff on a site called zzl.org. However, this attack eventually led to the attackers gaining root on a server called svn.apache.org. Long story short.
It's their source code control. So they basically had not just the source code, but like they could make changes to the source code of the most popular web server on the internet. That is what happened.
We want to do that too. It's kind of impressive, and this was the first time for me where I saw that XSS could have a potential beyond, the basics. This modus that they used became, or that this attacker used, became popularized. It was found out after like 4 or 5 days that this had happened, but the finding out is almost always random or circumstantial. So every time someone finds these backdoors, it's almost always because of some random stuff. Like here, they sent out a lot of reset password questions to people. Need to speed up. All right. Seen this? Off-brand stuff. This is what you do in typosquatting. So in typosquatting, you're trying to take over packages by misspelling things. Like you maybe want to appeal to the dyslexic people, or you just make a name shorter or something like that. Here's a picture from a talk called Towards Measuring Supply Chain Attacks, etc. This attack, or sorry, this shows a graph from 2016 to 19. And in 16, a young man called Nikolai Chacher wrote a bachelor's thesis where he hacked 17,000 machines. So maybe someone from the university was really happy about that. So he hacked literally 17,000 machines by supplying fake packets on Ruby, PyPy, and NPM. And because he made instruction for that, 1 year later, real attacks started popping up. Perhaps. Maybe it should have happened without him, but it happened a year later. You saw a spree that still hasn't ended. It's just going on and on and on. And what is noticeable maybe is that Ruby comes in the end of this. Ruby was late in exploitation, PyPy and NPM was early in exploitation. That's important because it's easier with PyPy and NPM. It's harder with Ruby. You have to have a bit more brain thinking to get there. As a comparison, Java is even more hard. But Java has more valuable targets, no offense to Python developers.
Half of the society in the Nordics is relying on Java, basically.
We don't talk about 2020, but in the end of 2020, something really terrible happened, obviously. These 3 artifacts were uploaded to Maven Central. One called Maven Compiler Plugin. Guess what that one does? It's a Maven Compiler Plugin. It's a colliding name with the original one. There's a Mail Watcher plugin, was meant for Jenkins, and Servlet API, which was made for Tomcat. These plugin codes were downloaded 800 times during a period of like 6 days. So perhaps someone popped 800 shells, but in this case, they didn't pop a shell. They did something much smarter. They went for arbitrary code. So in a disassembly, this is what it looked like. They made a download of a JAR file, and they made a class load, which is the right thing to do, according to us. And in doing so, they got arbitrary access to 800 random machines. And the attacker was never seen again. Let's briefly talk about bit flipping. Apache.org serves the internet with Java files, JAR archives. That's the registry we talked about. We don't own the domain apache.org, but we own the rest. This Friday, you will see more about bit flipping. So maybe
our good friends, Stök and Juhoy, we'll talk more about this tomorrow, and they did at Black Hat. Really go watch their talk. They can explain much better what happened. This blows my mind. Like, I didn't believe this was a thing. But now I do. It's absolutely crazy. Anyway,
so what's going on? Once the zeros on the screen, right? We registered these domains after hearing about this. And if you just change 1 and 0 from apache.org, you get arachi.org or whatever. And so the computer just needs to make one single error to reach us. And like I said before, we want to hack apache.org because it serves the entire internet with Java packets, because Maven Central uses it as its repository. And sometimes mistakes are made. Here's a mistake. It's a mobile device that tries to download something called a Maven metadata.xml file from repo.maven.arachi.org, which we own. And in doing so, we could have provided a different XML file showing them where to download a JAR file, etc. This is not a Maven client. We were surprised.
Yeah.
Because this works for mobile devices and some other devices for us, but it didn't almost never work with a Java application. So we didn't catch any Java applications, and this was, frankly, maybe not our primary attack path. But it was interesting. And it felt good to own the domains.
Yeah.
And the domain names can also be used for typosquatting. Lastly, okay, account takeover, well, that means that you basically just take over someone else's account. Everyone knows that. So if you go to rubygems.com and you start brute forcing someone else's password, you just try a different password based on known lists of passwords that this person has, you might get lucky. Someone did and took over REST client, which is back then the most popular HTTP client in Ruby, and served a Bitcoin miner. Boring, but they did. Maven Gate is like buying an old house just to get access to the mailbox. Java was built in the beginning of 2000s, the Java landscape was, and it's based on, if you own a domain name, you can register a packet at the registry, but you need to own the domain name. Problem is, the companies that built Java are gone, and their domain names are expiring now. So if you register their domain names now, you can take over the packets now. That's basically what this means. So if you go to jitpack.io, you can sign up, because jitpack.io is an alternative to Maven Central, and you can go there and register your domain name if you want to. Are you convinced that it's possible to take over a dependency? Yes. Thank you. Okay, then we can move on.
And everybody's seen this one, right? I mean, we got to show it. This happens a lot in development. Like somebody uses dependencies, the transitive dependencies, and way down the line is somebody who's maybe like forgot their password to the project. Do you know exactly what dependencies you have and who maintains them? That's a question.
Yeah,
I
don't see much head nodding, but a lot of this.
So you need to be...
Yeah. This was raised 47 years ago by Ken Thompson, who invented C and many other things, but he made a paper called Reflections on Trusting Trust, posing this question. So if we're compiling things, how can we know if the output data is actually what's being made by the compiler? And that's something that Typosquatters abuse. I mean, this essential question. We rest, obviously, on the shoulders of giants, because everyone's done everything cool already. Everything's been done. But Jeremy Long wrote the Java dependency checker, the tool you use to show what dependencies you have. That's the one everyone started out with from OWASP. He also wrote a talk, or made a talk at Black Hat in 2023 that you should watch, that shows something that blew our mind.
Yeah, so basically, he came up with a way of doing the same thing that people did in PyPy and NPM, but in Java. Like, that's pretty novel still.
And this broke our assumptions, because we didn't think that would be possible, really.
Yeah.
And that's what got us down this huge rabbit hole. In this case, you see a dependency from Jeremy Long called Spring Analyzer. That's the bad dependency. Remember that, because in the coming demos, we're using that as a bad dependency. We'll remind you, but still.
You need to speed up.
OK. Right.
It's fine.
In this demo, we're actually using exactly what he did, and we'll just show the demo of what he did for us. So he shows that if you build a Spring application and you add just a dependency without doing any of the code he's using, you can still inject your code using only the dependency, using something called the build helper. And this assumption is something that helps us. In this case, I don't have really good access to Maven, so it doesn't resolve all the dependencies for me, which means I need to copy dependency information from the internet into a POM file. A POM file contains the dependencies.
This happens all the time, by the way. Developers copy-paste, they go to Stack Overflow, ChatGPT, but how do I have a dependency? Like, this is common.
It doesn't work. I hate when it's red, and it's red.
Yeah.
And now I need to copy-paste something from the internet, and ChatGPT or someone else told me to copy something, so I copied something. And it's not red anymore, so everyone's happy. Woohoo!
And you ran somebody else's code.
And we got Spring Analyzer as part of it. But well, it's not easy to know that this is a vulnerable thing. So it has a build helper, which means that anytime I build something against this jar file, it will contaminate the build for my output. One contamination for one output. And now I run the code. And obviously we are, well, popping a shell.
Popping shells. You gotta do it. Anyway. So that is Jeremy Long's research, not ours, by the way. We will iterate on that.
This is real. Exed did the exact same thing, using social engineering, copying things from the test path, getting it in there. This is exactly what happened 3 months later with Exed. It was a pretty brief warning, but, well, the attackers did fundamentally exactly that, working with one single target. Let's talk about cross-build injection.
So cross-build injection is a concept where your build, say in a build server somewhere, could potentially, if it contains malicious code, spread itself somehow to other builds, right? Depending on how you build your build environment. That's the concept. And Maven has this thing called it's like a local cache you can think of, a local repository, where it writes to all the time. It's its cache, it reads and writes. You know, blue teamers, this is noise for you, I'm sorry. But if somebody pushes something malicious to this build server and it maybe infects things on this cache, it's kind of like a Maven cache pollution, maybe? I don't know. Then that could be possibly very, very bad.
And the build server now turns into this bad character. It happens to all professionals. So clearly they can steal our credentials, right? They can steal the code too. But what happens with the builds?
All right, yeah, sure. So if you have execution on a build environment, you mentioned there's going to be credentials there. You might infect everything on the other build pipelines. So that's actually a form that's a lateral movement in our world. Like you're going from one innocuous app to like the production app. And when you start to infect things so bad in a build environment, like that's also a form of persistence. And remember, this is not modifying the source code. Developers will go to the source code and read the code, and there's nothing there. But then they pushed it to the build environment.
Thank you for pointing that out. That was a 2000 thing to do.
Yeah,
in 2020, we go for build outputs, not the source code.
Nobody will find that.
Let's look at the demo.
Sure, demo.
This is a demo in 2 parts. Alice is having fun day. On a fun day at Jerkeby Security, you can do anything you want. And she certainly does. So she goes out to the internet and downloads, Jeremy Long Spring Analyzer. This time, we spiced it up.
Extra spicy.
This extra spicy version is now being built into her Fun Day application. And now we're sharing the same Jenkins server for Fun Day and production stuff, because there can only be one. And if you look at the console output over here, and you also try to look at this burp thing going on there, you will soon see pingbacks, because during build, while this is compiling, our code is executing.
Our malicious arbitrary code.
I mean, the program isn't even running yet. We're already executing whatever we want.
Yeah.
And
so we actually exfiltrate some stuff from the build server here.
Yeah,
you can
we're already on the build server during compilation.
Yeah.
But also, it starts now to infect all build outputs. Everything in the Maven cache, in the Maven repository, is now contaminated. Which means that whoever comes after is in deep trouble on this entire Maven server. Cleaning up is hard.
Yeah, and this is Bob, right?
Bob is a serious developer on a Monday, pushing to production. But Bob does not go and download the Spring Analyzer. Bob knows better. If you look at Bob's dependencies eventually, now he's pushing to main, and it's going to trigger a build job in the production environment.
Yeah, he's doing a new feature on Monday. He has nothing to do with Alice. He's like, yeah, that's fine. Push, to my CI/CD pipeline, as I do always, right?
Bob doesn't need to look in the POM file because he didn't make a change even. The commons.io was always there. It's always on the server. But now he is taking a peek. Common.io was infected just now by Alice on Fun Day Friday.
Yeah.
And once again, the attacker looks in their burp log to see what happened to this build. And now it doesn't matter what you do in this server. Anything you touch on that machine will turn to garbage. It's spiking everything. It's re-spiking everything. So it's planting itself into anything there. If you cleaned up, it's going to make a mess again. If you run any Java application, compile anything, it's going to be a mess. Imagine how many times we had to record this.
Yeah, and if this is like pushed to a repository and somebody else uses it as a library, oh fuck, it's all over again. Like, this is a mess to clean up. It's bad.
Yeah. This is all his work.
I get to be the bad guy, I'm sorry.
But imagine the time it took. It was like, wasting a lifetime. Anyway, this has actually already happened in reality. There has been attackers who have done this before us. And in NetBeans, there was a plugin called Octopusscan, and it polluted jar file outputs if you use NetBeans, which is tiny, tiny IDE, not compared to IntelliJ that I just showed you. Anywho, just so you know, attackers know about this.
Yeah.
We did not invent this. And also, we're not giving this tool away. Just so you know, we're giving this away.
Yeah, all right, cool, JarPlant. So I like to code, we both like to code, and we want to give you a bit of a gift. Who doesn't like that? Nice. So we want you to go back to your organizations, your clients, and test this. This is important. You need to test for this stuff before somebody else does. It's on the horizon. So we want to put a tool in your hands that red teamers can use with consent to basically infect the thing that we showed. Like, maybe we can... Yeah, we have a demo for it, right?
Go ahead.
Can you play it?
I'll press play.
All right, cool. So here we have 2 terminals, and one of them is like, I have the testing app on the left-hand side. It's just a test app. It does some diagnostics, output, and pretends to do something, and then it terminates because it's a demo. So that's the normal state of it. And then you got JarPlant, this cool new tool on the right-hand side. And we're going to run it, use the class injector, and point out the target, the test app, right? And we have an implant called DNS beacon implant. I can explain it later. That takes a configuration parameter of a domain name that you can control. So this is like your burp collaborator. I use interaction in this case, copy-paste that one. And that's going to be a part of the implant into the test app. And also, I like the bug output because that's cool.
Exciting.
Exciting. So there you go. It did stuff. You see some verbose output. You see the implant type, the target, and all of that. And it's actually imprinting the configuration parameter into the Java bytecode that it's inserting. So that's pretty cool. I'm proud of that. But essentially, this is complicated. It's not just inserting a class file into the jar. It has to modify the bytecode of all the things in the jar to actually trigger. We can have an entire talk on this one, but we're out of time. So, and you see, they've successfully spiked the target app.jar. It's a spiked jar now. And we'll run the same app again, and what happens, right? Boom, enter. You see the same thing, but the implant also triggered. Holy fuck.
First, also, before anything runs, you run.
This could be a library. It doesn't have to be an executable. Like, this could be a library that somebody used it. And when they use the library code, boom, triggered, right? And we see in our interaction out of bounds thing here, we get like a big DNS query back. And we have a decoder even for the JarPlant where you can decode this.
So essentially, he made a C2 for it as well.
Oops. And you see, like, this is some output of like the host name. I use a Kali instance here, but like, and some other thing. And this thing could also, like, if you do this on a build server, like, this could exfiltrate API tokens, credentials to your cloud, your Kubernetes, whatever, your repositories. Like, it's all there on the build server, right?
And by that, please go ahead and try this. We are approaching the end of our time. Don't be strangers. You can find us in the bar, obviously, because we have spent a lot of energy on this and we're almost drained. I'd like you to look out for this potential in the future. I know that a lot of you actually do run Java environments in this audience because I know most of you. And these environments are very sensitive. They're unprotected against this, and we should have a discussion about how to do that. We're out of time, unfortunately, but it's really, really worthwhile thinking about this potential because we know people can do it. It's been done. You can now also test it, so it's not just them who can do it, which I think is a good thing. And if it's already happening right now, which it very well might be, we are going to start to detect it now that we know how to test it ourselves. So please go ahead and do that. And thanks for listening.